Oops. There we go. Anyway, again for HQ, if anybody has any ideas and would like to contribute to JBIS, Chronicle or Spaceflight with new papers, articles or website material, they'd love to hear from you. So please contact the HQ or the editors for some information. Membership, also social distancing. Again, about two-fifths of you here today are non-members, and about half of you are return. You've been here to a few of our events. So I think you're missing out. If you become a member, we've got literally hundreds, if not thousands. I'm not sure if it reaches thousands of hours yet, but of talks, lectures, symposia, conferences, all the HQ ones, some really big names all the way through. You can binge watch that as soon as you join. I know I did. I disappeared for weeks on end doing that. You get Spaceflight Magazine or JBIS or Space Chronicle, depending on what you sign up for, monthly newsletter, and there's lots of other things. There's lots of projects and things you can participate in as well. Lots of stuff on the new website. So I'm just going to move on. Yes, if you believe like we do, the frontiers of space are there to be explored, please do join, and I'll put the link in the chat later today as well. So without further ado, Paul, I apologise for the photograph. It's the only one we could find. So we've got Paul Jackman and John Harlow. Actually, I'm going to let them do the talking. So they're going to be talking about Chevaline Polaris post-boost propulsion system, the twin chamber propulsion unit. And without further ado, I think John's going to kick off and give us some background. So I'm going to stop sharing and find your slides, John. Does that work, John?
Yeah, thanks, Bob. Well, this is, just say hello to everybody. Some of the old faces I haven't seen for an awful long time appearing on the screen earlier. It'd be nice to have a chat with them later. This is a very short presentation to lead into Paul's. What I've done is condense the presentation I gave, two and a half years ago on Chevaline. So effectively what I'm saying is it's a little bit of the why this was required to set the scene for Paul's discussion later. You will see the last bullet there. There's a question mark with no word against it. Well, I didn't quite know how to describe the last option that Westcott decided to look at as a propulsion option. We'll come on to that. Next chart, please, Bob. Okay, a lot of people will know a lot of these names, a lot of these dates. I think there's a deliberate mistake there. Maximum range was only just acceptable. I don't know why that slipped through, but it did. I think the key issue there is the bottom bullet with the low beta, the penetration speed of this type of re-entry body, having that low beta really slows it right down and makes it much easier to intercept by whatever you want to intercept it with. Next chart, please, Bob. Okay, so that's the point there. Terminal velocity is quite low. An easy thing you could do was to have high beta bodies replace the low ones and come in much faster, giving the defence less time to react. A couple of other points there is that the ABM treaty there that I mentioned, the lawmakers really screwed up there. Just to remind everybody, 100 launches doesn't mean necessarily 100 missiles, but the dear old lawmakers didn't realise that. And studies that we did showed that those launches could be reloadable. So it wasn't 100 missiles, it could have been 200 or 300 or whatever, protecting Moscow. The other interesting thing was that SA-12 type, SA-12 plus type systems could be fitted with a nuclear warhead, and the effects of high altitude detonation were unknown against an REB. And when we did get access to that data, it didn't bode well for the survivability of the REBs. Okay, so what were the options? We needed more sea room for the boats, submarines, sorry, nobody calls them boats, I suppose, if we're on Civvy Street. We could have had Poseidon missiles backfitted into the Polaris boats, but the whole life was running down anyway on those boats. So obviously, if we had newer boats, we had more scope downstream. Clearly, high beta, we just mentioned that one. The numbers game of the warheads, it's a clear that if we had more warheads to throw at the nasty enemy, he would have to up his game in terms of the defence. There's other things we could do, multiple re-entry vehicles, independent re-entry vehicles, blah, 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 aeroballistic re-entry, etc. But the UK wanted to keep the numbers down for cost. So we were stuck with politically, I guess, economically, we were stuck to low numbers of live warheads. So the question was, well, you know, if you have a lot of warheads, you either go all live or you have live plus decoy to soak up the defence, and you can use so-called null range vector. Now, the thing about NRV is that it's effectively a volume in space. You can think of it as an arced or curved tube. It all collapses onto the target. So if you fill that tube up with decoys or live warheads, then the enemy sees all this stuff coming in and doesn't know which one's which. So, but just to remind everybody on the bottom line, I suppose, is that the missile's job was to lob the sea body at the target and then release the pack. And it was the pack's job to fill up that area of the null range vector with whatever it had on board, all the disguises, and of course the other P-body. And it was the pack's job to move up and down the null range vector, filling that space with whatever the pack wanted to deliver into that space. So we needed propulsion. Next one, please, Bob. There you go, what to do. So the requirement was for 3 repositioning burns. There was no requirement, I believe, on the reliability of the last burn necessarily. But one of the things we were told time and time again was that we had extremely high sensitivity and security in respect of what those burns should be and their variability. But we had to control, variability is not a good word, but we had to control precisely the burns, but they could be variable in length. So looking at the options, solid propulsion there, we had very restricted space, and I think that's a thing that Paul will probably bring out as well in the liquid TCPU. The propellant mass and therefore the total impulse is fixed as soon as you've filled the motor itself. And the only way we could try and meet any of those requirements was to have a rather long cigarette burning charge that obviously gave the pack a bit of a problem in terms of the change of centre of gravity that system would have given the pack. Unacceptable change. Liquid propulsion, well, I won't say much about it other than in terms of the burn times, the differing burn times required on that particular flight definition. You could put it in electronically, and this the mission itself could be fed in from the electronics package pretty late in the mission. The last question mark I had on the first slide was the inselect motor. I'd almost forgotten this one. Paul will probably remember, and I think Mark will as well. John Taylor carried out a series of tests on a solid motor, effectively, that we then used injections of liquid into for the second and third burns. It worked, but it would have required an awful lot of development, shall we say. It was too long, probably too expensive in their eating up too much time.
Very large mass penalty as well with that.
Yes, indeed. Yeah. So in other words, the best option out of those to enable a very late fixing of the flight definitions, we opted for a liquid. And if anybody sees a D9 motor referred to in terms of Chevaline, they will know that it was the solid propulsion option that was cancelled in favour of the TCPU. That's it, Bob. Thanks very much, chaps.
Okay. Well, I'm Paul Jackman, an old lag from Westcott. I still live 3 or 4 miles from the site, which is my home village. So I still visit the site quite often, but I'm very interested in some of the sessions you've got, especially with James McFarlane and the NAMO people, just having worked closely with them. and in fact starting my career on J-Site, where James now works. I'm going to do this from memory. I'm not a great collector of history, but I have got a memory, and I'll get my excuses in first. Some of the stuff I'm going to talk about was 50 years ago, so I might make some errors due to a poor memory, and if anyone has anything to correct my memory afterwards, I'll be glad to hear that. That would be great. Next slide, please. I don't think these slides have been pre-distributed, have they, Bob? So I'll just run quickly through here. There'll be a brief introduction about myself. Then I'll talk about how these liquid bipropellants came to be at Westcott in the first place, describe them in some detail, then go on to how the technology of that was developed, and leading on to a test vehicle program called PLTV, Packageable Liquid Test Vehicle, which was very successful and demonstrated a whole range of technologies which eventually got incorporated into the T11. I was on the Lance procurement executive in main building, I think it was main building, and that also led us to understand some technology and in fact borrow some essentially. And so therefore, having done that, we were prepared for this T11 development when the requirement, which John has adequately described just now, when that requirement came along, we were ready. And then I go on to describe that. And I'm trying, in this, the 50th anniversary of Prospero, throughout this, I'm trying to develop a theme whereby we mustn't abandon technology because there's no immediate need for it. We need to keep a technology basket available so that systems designers can call upon all those as it goes along. And I should try to develop that theme a little as we go through and at the end. Next slide, please. Right, having graduated in mechanical engineering, so any chemists amongst you, go easy on me. I joined Westcott permanently in 1967, having spent a summer student period there, and immediately joined Liquids Division and worked on the empirical injector and thrust chamber development. In liquid propellants, I have only ever worked with hypergonics or monoprops. I've never worked on any cryogenic materials. Also did some work along with Dr. Bernard Bonner, who lives in the next village to me now, on safety aspects of those, so that we were developing the understanding of how to handle this stuff and how to handle mishaps with this stuff. I was a firing officer on quite a few sites, fired engines, and then through a natural civil service progression, ending up as a Royal Ordnance Rocket Motors Division Chief Engineer. Westcott, of course, was the centre for virtually all, if not all, UK liquid propellant work. So when this requirement that John described came along, it was inevitable that that would be done at Westcott. Next slide, please, Bob. Right, hypergolic, not hyperfolic. John did point this one out, and I've corrected it on my card copy I've got in front of me. Blue Streak was cancelled in April 1960, and thereafter we did continue doing some liquid hydrogen work at Westcott. In fact, Westcott was the first European source of LH2, the plant being designed by Dr. Trevor Horton, an old friend of mine. But that all got cancelled in around 1969, causing Dr. Barry Ricketson to resign from the company, set up his own company called Cryogenic Calibrations. So we were now in a kind of a void. And then Dr. Dudley Lewis was appointed superintendent in 1965. And the rumour has it that on his desk was an instruction to close down Liquid Engines Division, or Liquids Division. But he determined not to do so. And he was aware of, and we became aware of, a lot of work going on in the United States at JPL Pasadena by Jack Roop and Riebling, and at NASA Lewis and in Rocketdyne. They were all developing hypergolic bipropellant work. developing that technology. So we determined, and Dudley persuaded the powers that be, that we should do this. And so a decision was taken at around that time to do work on hypergolics, but and in parentheses, not to include into halogens, chlorine trifluoride or even chlorine pentafluoride was looked at in the United States. We decided that was too hazardous, and quite rightly so. And so essentially we developed this technology, and it became a solution looking for a problem, which is an ongoing theme. Next slide, please, Bob. Oh, I see now what you mean about the G and repositioning, John. When I print it on my computer, that doesn't happen, but that's by the by. The repellents that we chose to look at were inhibited red fuming nitric acid, which is essentially nitric acid plus some NO2, and the inhibited part is HF, hydrofluoric acid, which is in there, and that acts as a passivator. It rapidly attacks the tankage containing, which is usually an aluminium alloy, and forms a very, very tough fluoride layer, and that prevents further degradation and attack of the acids on that container. Thus, you can store earthner in an aluminium tank for many years, and we've demonstrated that by laying stuff down and checking that out. The propellant, the fuel that we chose was mixed amine fuel 1, MAF1. And in checking on the internet a little while ago, I found that the mil spec for this was cancelled in 1983, which shows again how old all of this is for me. MAF1 comprises 85% monomethyl hydrazine and some hydrazine itself, plus some diethylene triamine, which I think is probably in there as a viscosity index improver, but I'm not sure about that. Red fuming nitric acid naturally is extremely corrosive. When we're working with it, we use the mantra, if you get something in your eye, you're blind. You have to be very careful with it. MAF1 is corrosive and potentially carcinogenic, but the hydrazine itself is extremely carcinogenic, and of course we use that much later on in the Chevaline program, in the Hydrazine Actuation System, which is the AOX for which Mark has just described as the suborbital spacecraft. It has an operational exposure limit when I was working of 0.1 parts per million. OEL, it means you can survive in it, I think it's 8 hours a day, 5 days a week. A feature of these bipropellants is that they are hypergolic, in other words, they're light on contact, even at room temperature and pressure conditions. The ignition delay is around 3 milliseconds. It has been measured various ways, especially at JPL, and is around 3 milliseconds. That 3 millisecond delay, while it's mixing, means that you can exploit a liquid phase mixing, and that's what a lot of my empirical work was done on. So you mix these propellants prior to ignition. This makes the combustion process very, very efficient, and it's completely different to what you would do with, say, liquid oxygen kerosene, where you would atomize the two propellants, ignite them, and then you would rely on vaporization, gas phase mixing, and combustion. This is quite a different technology, and you'll see later that the injectors that we use exploit quite different phenomena than you would use in a LOX kerosene engine. So it's nearly always, in fact, exclusively, they are impinging streams, whereas for the earlier propellants, you use shower heads. Next one, please. Right, so what we set about was, and John wanted me to try and put some names in here, what we set about was developing these technologies in various sectors and sections. And we had actually adopted what we didn't know it as such, but it was actually a matrix management approach, something which in my later career as leader of various major programs I was very keen on. So each person had his own line management, but he was also responsible to the group leaders through these activities. So, for example, in propellant handling and safety, it was Dr. Bernard Bonner, a chemist, a very fine chemist, as I said earlier, still lives in the next village to me. Expulsion tank design. Expulsion tank design was a guy called Dr. George Cook, an Australian, who I last met at Bernard Bonner's 50th wedding anniversary. We all live close here. Valve technology, Mr. Frank Henderson. Frank developed a lot of the T11. He was responsible for quite a lot of the subsystems. I led the injector thrust chamber design. Solid propellant and isopropyl nitrate gas generator was Dr. Alf Hardacre, and John Rolfe led the solid propellant development to those gas generators. Overall vehicle design, this is when we flew the PLTV, and later on when the overall design of the T11 was under development. That was John Orton and Alan Cruttenden and a company called Bristol Aerojet down near Weston-super-Mare. That factory is now a housing estate, I believe. Design detail, and obviously in the design office. Flow control, as well as valve technology under Mr. Frank Henderson. We used cavitating venturis to control the flow of propellant into the engines. Cavitating venturis, whereby you accelerate the propellant until it actually cavitates, and then you recover that pressure. It means that the flow through the cavitating venturi is independent of downstream pressure. And that was very important in T11, as we'll see now, because of the need to control centre of gravity. Malcolm Paul still works at Westcott. He was the lead test site guy. Engineering aspects, Dennis Ripp, Bristol Aerojet, Mr. Chris Saunders. Mathematical modelling was Adrian Mead. And instrumentation was led by Graham Harris, and we developed the WEDRAM, the Westcott Experimental Electronic Digital Recording and Analysis Machine. And then there was also a materials department and Peter Dudley. So all of these people were working together with one aim, which was to develop a technological basket, if you will, that future requirements could select from. And that turned out to be successful. Next one, please. Right, the PLTV program, and John suggested we might have another session on this, was extensive. It can be summarized, it is summarized in that paper there. John has a copy of that I sent to him. Unfortunately, because of pressures of Chevaline, Alan and I could not go to Las Vegas to present it, but never mind, I don't particularly miss going to Las Vegas. But it was a series of flight vehicles, and it followed subsystem demonstrations, and there were flight vehicles flown out of Aberport in Wales, and it provided the basis of the T11 design, an all-welded tank piston design we'll describe later, pulsed firings. Not only were we doing variable duration firings, we're actually pulsing the engine. Poppet-type propellant valves, which went on to Chevaline. For the pulsed engine, there were also butterfly valves, such as you might find in a petrol engine. Demonstrated isopropyl nitrate gas generator, which was discontinued for Chevaline in favour of hydrazine. Demonstrated the impinging jet injectors, the ablative combustion chamber insulation, which is very important. It's a simpler way of keeping the combustion chamber cool rather than the usual regenerative system, whereby the fuel is fed through the combustion chamber to cool it and then regenerated back into the combustion system. And refractory nozzle throat inserts, which is also very important for Chevaline because of the need to maintain pointing accuracy. Next one, please, Bob. Right. At this time also, there was a packageable liquid engine being developed for the Lance program in the United States by Limtenko Vought. Lance is a tactical nuclear or conventional warhead vehicle, and it replaced the Honest John. I had the pleasure of going to 2 weeks in practice camp in Lunenburg Heath and actually witnessed an Honest John live firing, which is quite exciting. But the Lance replaced that, and the engine was developed by Rocketdyne, and it's very complicated. It was a pair of engines that were concentric with each other, and the flight profile was such that the boost engine would fire, and it was spun to maintain accuracy, just like you spin a bullet through a rifle. Spun by, I think it was bleeding gas off the solid propellant gas generator, and it basically put the missile into a predetermined position, and then from then on, the sustain engine was infinitely variable, and it was flying thrust equals drag. So it's flying a true ballistic or a mocked up ballistic trajectory. So you could very accurately determine where it was going to land. It was an enormously difficult thing to develop, but they did develop it. It used earthner and unsymmetrical dimethyl hydrazine, which is similar to MAF1. But reading across from that engine to the Pltv Tcpu was a solid propellant gas generator in a concentric configuration. One of the Pltv engines or vehicles did have a solid propellant gas generator concentrically designed into the fuel tank. The expulsion system design on Lance also read right across, and all the difficulties they had there, we were able to learn from those. And the whole thing was a silica phenolic ablative combustion chamber insulation, which we exactly put into T11. So again, the theme here is be aware of technology, make sure you're up to date and understand technology wherever it might be from. You never know, it might be needed. Next, please. So the preparedness we had developed for the T11 development was we had a hypergolic bipropellant technology program well underway, well established through the flight test vehicle. Unbeknowingly, I think, we had developed a management structure for Chevaline. It was a true matrix management structure with the ultimate control, of course, being in main building, London. But there was also Farnborough, Aldermaston, and contracting companies involved in all of this, and we had to learn to work with all of those. And we read across from other USA missile programs and became familiar with USA technology programs. I mentioned earlier Dr. Trevor Horton, and I shall mention him again later. Trevor spent 3 or 4 years in the British Embassy in Washington, and his role there was exactly that, to become familiar with USA technology and to bring that familiarization back to UK and especially Westcott. And that was I applied for that post but never got it, unfortunately. Moving on, please. Okay, so we've now got the developing technology available to us, but we've got to try and put something together to do what John described earlier. And one of the major constraints was the space available. So John, Bob, if you can flick forward to the next picture, please. This is a penetration aid carrier. The gold bit sticking up the top with the brown bit sticking out the end of it, that gold bit is a TCPU tank with its secondary containment, and I'll describe that later. And the brown bit sticking out the top is one of the nozzles. Now you can clearly see there is just no room to do other than package this stuff as tightly as is possible. And by the way, the silver tank on the right is a hydrazine tank for the hydrazine actuation system. And immediately to that left, that brown cluster is a rocket engine module. That's 4 hydrazine monopop thrusters. John, I think I gave you one of those as a memento. That's just a by the by, but you can see how very tightly packaged this is. Those tube-like devices are where, can I say, John, decoys are thrown out of there by very, very complex little rocket motors. They're combined axial and spin thrust, all developed and produced at Westcott. So it's an enormously difficult job to fit all this together. And fit checks was a very important part of developing this thing to make sure it would all go in there. Can we go back now to the previous slide, please? So we looked at various options. We had to provide elements of thrust or impulse before and after various items have been expelled from the system. And so we had to aim at more than one position on the vehicle. So we looked at vectoring one chamber. Now we've never done thrust vector control of a liquid propellant engine before. We looked at vectoring the whole issue, but it was just too complex. It was untested. Control would have been a nightmare. So that was rapidly thrown out. Various tankage solutions I can remember were looked at. I can remember examples of canted tanks, fuel and oxidant tanks with different diameters, different shapes, different sizes, all kinds of things. But in the end, again, we found the most volume efficient way was to have parallel sets of tanks. A solid propellant gas generator, external and internal, was looked at. Sperry gyroscope at Westcott at A site, Westcott, or the B site. We're trying to develop the AOX system using isopropyl nitrate, and we were looking at trying to pressurize the tanks for the T11 out of that. But in the end, that system became too complicated, too unreliable, probably not likely to work. And so we rapidly went to the United States and procured such a system based upon hydrazine. We also looked at pressurizing it from an inert gas reservoir, a tank of very high pressure helium, for example. But again, that's massive. It needs control valves and it's volume limited. So all of that was looked at. But in the end, we came up with the design we've got now. So next, please. Well, no, next again, Bob. Okay, other design challenges include, of course, safety. The Royal Navy are paranoid about liquid propellants, for good reason probably, and doubly paranoid when it's in a submarine. You can hardly blame them. And so the tanks had to be an all-welded construction. I've already described how, because of the HF in the earthener, there's no problem with long-term corrosion, but they had to be all welded to make sure that the thing wouldn't leak. And as a matter of fact, ongoing spacecraft engines that Namo build at Westcott now could be much cheaper and much more easy to develop if you could bolt them together, but prime contractors won't let you. They have to be all welded. We had to ensure that there would be 4 independent failures before you could mix the propellants internally. Clearly, if you do mix them internally, you're going to get an explosion. And this was achieved by having 2 gas inlet burst discs. The hot gas from the hydrazine system came into the center of a pair of tanks, out through a pair of burst discs, and then it welded shearings between the piston and the tank wall. So you had to go burst a disc, burst a shear disc, and then it would expel both sides. So if those were to fail somehow, you would get internal mixing. I can remember saying to people, how many tins of baked beans have you seen leaking in Tesco's? And do you think we build this to the same quality? But we still had to go through all this because of the paranoia in the Royal Navy. You had to protect against inadvertent firing. You never know what electronic environment you're going to be in, and a lot of the startup would rely on pyrotechnic valves. So the Haas prime mover was in fact a helium tank, and that had a divert valve fitted to it, so that should it be activated, the helium would just be dumped overboard. And the first thing that would happen when the system was to be activated is that divert valve would be changed to make sure that it could do the work that it needed to do, the helium, that is. There was a liquid propellant leak detection system in the submarine. This required that if the tanks were to leak, then you would be able to detect that leak before it became a contaminant in the submarine. And to do this, around the T11 tanks, we put fluorinated ethylene propylene bags. Those FEP bags were made by a company called Holscott in Grantham, and I think they're still trading. FEP, of course, fluorinated, anything fluorinated is essentially inert. But this is a great example of overcoming one obstacle and creating another. Having decided to put these secondary containment polymeric bags around the tanks, we realised we now got an electrostatic hazard. And so the things have to have a conductive coating on them. Now, to put a metallic conductive coating on an FEP surface is no mean feat. But it was done by a company called, actually it was a research company called Fulmer Research Institute at Stoke Poges near Slough. And they found a way of putting a thin gold coat on these bags so as to make them conductive so that it could be earth. And when I showed you that previous picture, the gold-looking bag sticking out the top is in fact gold. The hydrazine actuation system had inside pipes. It had hydrazine sensitive sensors, which worked by a polymeric film dissolving in the presence of hydrazine and activating a switch. So all of this was monitored by the submarine, and later on I'll show you some of the pipe work associated with it. A very complex system, but it's notable that because the Haas was developed and purchased in no time whatsoever, and by the way, it was purchased in an unrestricted, from a security point of view, environment, which also limited it quite a large extent. It had no secondary containment as such. Should any of this complicated system create an alarm for the captain, then his palliative is to simply flood that missile tube with seawater. What happened when they got back to Cool Hawk with a missile tube flooded with seawater, I'm not sure, but that was the palliative. Of course, it never happened. The TCPU, or T11, when you think about it, it was either in manufacture at Westcott or final assembly at Westcott, including the filling, or it was on the road being transported up to Royal Ordnance, RNAD, Royal Navy Armament Depot, I think is at Coolport, or it was in storage at Coolport, or it was in the very benign atmosphere of a missile tube on board one of the 4 submarines. Turns out that the most rigorous environmental part of that is actually the road transport. What happens if there's a road transport accident on the M6 or somewhere? And so the container that we transported that thing in was a major piece of engineering. it was soft mounted. It had leak detectors in it. It had shock detectors in it, and accompanying it along the road was a so-called detanking trailer. Mr. Cliff Saund, who worked directly for me, was the lead designer on that. This meant that if something went wrong, you could actually take the propellants out of the Tcpu safely at the side of the road with this incredibly complex detanking trailer. All of these aspects and many more were all subject to very detailed, very thorough SRTs, slow run-through. Those SRTs were done either as demonstrations at Westcott, simulating doing it at the side of the road, for example, or actually at Coolport with the operators there. SRT was not only done for these aspects, but it was done for all of the aspects. It was a major part of the program, slow run-throughs. Another design challenge is, should the seals on the piston that's expelling those propellants, should they leak, then there is potential for those leaked propellants to get back together and maybe ignite and cause an explosion. And so one had to make sure that on startup, especially on startup, you didn't get leakage. And to this end, and I'll show you something more about it, the seals on the pistons were U seals, but there was a pair of them back to back. The reason for this is that when the piston is broke, when the shearing breaks away, having been pressurized, it actually causes bounce, and you have to seal the tanks in both directions, and that was quite a major thing, and I'll talk about an aspect of that a little later. So safety was a major consideration, of course, especially as it was a naval application. Next, please, Bob. Right, performance proving. Obviously, we had to get as much performance out of this thing as we could. The better specific impulse we could get out of the engine, the less propellant we would need, the less propellant we would need, the less volume and mass we would need. So as always, performance is very, very important. This is kind of my area. MAF 1 is slightly higher performance than UDMH, and so much for hydrazine. We ran the engine at a mixture ratio, not ration, of 3.3 to 1, which is near stoichiometric. To get maximum performance, you usually need to be just on the oxidizer side of stoichiometry. The expansion ratio, again, not ration, was limited by space, and it was only 10 to 1 from memory. Now, this thing operated in space or near space, so the ultimate expansion ratio would be infinite, of course. But the more you can make the expansion, larger you can make the expansion ratio, the better performance you can get, the highest physical impulse you can get out of an engine. But that was limited to 10 to 1. And also, because of very, very difficult manufacturing techniques used, then it was also a pure cone. It wasn't a nice bell-shaped, which is much more efficient. It was just a straightforward cone. The combustion efficiency was derived by using impinging jet injectors. There were 30 elements. Each element had three jets of propellant. I've shown it schematically there. The fuel was injected directly from the valve. That was that component. No, that's the wrong way around. The fuel was a ring that slid over the oxidant, so-called spud, and it had 30 axial 1 millimeter jets. The oxidizer was in a pair of jets shown like that. And to get that, you have to make absolutely certain that you are causing those jets to impinge. If not, you might get neat oxidant going onto the wall of the combustion chamber and rapidly eating through the ablative liner there. So you have to make sure that you know where those are going, and you need to create a high coefficient of discharge through inlet profiling. You need to get a C of D up around a 0.7. And that's done by very careful inlet profiling. It was done by a company, I think it was Doughty Bolt Paul, I think are in Wolverhampton. And each triplet, so there's 30 triplets, and there's 2 of these engines per TCPU. Each one of those was checked that they would impinge where required, and it was done by carefully calibrated pins and so on. A very, very complex, very time-consuming, expensive, but very essential. Again, the space limit meant L-stars a factor we used. It essentially determines the dwell time in the engine. It's characteristic length, and it's the volume of the combustion chamber divided by the area of the throat over there. The larger that is, then the more time that the propellants have to complete their combustion. It's typically, this was all done in imperial units, of course. It's typically about 30 inches, but it's space limited. The bigger you can get that, the better, but again, we're very space limited. We used a high combustion pressure. I seem to remember the combustion pressure was 900 pounds per square inch, and the tank pressure 1,200 pounds per square inch. That is a large delta, but one way of making sure in these engines that you don't get instability is to have a very high or quite high pressure drop across the injector, typically about 20% of the combustion pressure. This will help suppress high frequency instability, and it will also help suppress what they call chugging instability, whereby you get a low frequency effect where pressure builds up in the engine, it blocks the incoming propellant, so it dies down, the incoming propellant goes in, and then the whole goes through a cycle. It's called chugging. You just stop that with a high pressure. The sea level specific impulse from memory was about 237 seconds, about 92% of theoretical maximum. It would have been higher had we got room for higher expansion ratio, but we didn't. And operating altitude is somewhat higher. And the thrust, I seem to remember, altitude was about 1,400 pounds force. Next, please. Right. Okay, I'm realizing I haven't described one thing. I'll describe as we go through this. Reliability. What we did, all subsystems were independently tested. So the Expulsion Subsystem was developed and tested by Dr. George Cook and his team on one of our runway sites at Westcott, 32 and 34 site. Frank Henderson developed the valves in 433 building and the flow lab, which no longer exists. Westcott. The thrust chambers are developed with help of Fred Nicol, who John mentioned earlier, and Cliff Saunt at C&D sites. And the filling and assembly techniques, A and B site, with people like Jeff Stanley, Chris Saunders. I'm going to describe the thrust chamber that I mentioned, the ablative thrust chamber liner. What it is, you take a silica mesh, a silica cloth, essentially, impregnate it with phenolic resin and cut it at 45 degrees, which is exactly like bias binding that you might use in making clothes. You can then wind that edgewise onto a mandrel. So you've now got a structure of silica phenolic which is edgewise on, so that if it tries to ablate, it's ablating through the lines, not layer by layer. And that we got that from the Lance program. It's then cured in a hydroclave at very high pressure, and the silica gradually melts and forms a protective layer, a silicon layer on the combustion chamber, and it flows through in the boundary layer. And when you stop the engine, you will find this silica will freeze as the engine stops, and you'll find it hanging out at the end of the nozzle. It's quite an interesting thing to look at. So that's, I'm not sure that I mentioned that, but that's where that comes from. The technology was developed at BAJ. It was improved at Westcott, and I do know how, but I won't go into it. It found its way into a much later solid propellant program. Reliability was also ensured by having PTFE slipper rings on the pistons. You don't want those pistons to be juddering at all. You need a nice smooth flow of them. Remember, this tank wall, after 10 years, has got an aluminium fluoride layer on it. So you want to make sure you're going over that nice and smoothly. And we also put nozzle closure discs. So the nozzles had closure discs bonded into them. This was mainly to prevent foreign bodies getting in there. But at altitude, it's probably best to ignite not under very low pressure. It will ignite under very low pressure, but it's more reliable if you've got the atmosphere in there, which these closure discs ensure. The subsystems are gradually integrated and tested at F-site. I'll show a film later of an integrated test at our F-site. And then the final assembly was tested with the gas generator from the hydrazine system. The hydrazine system had a gas generator on it, whose only duty was to pressurize the T11. It was called the high-level gas generator. We tested that at E-site. And quite interestingly, the first test that we did it wrecked it. It wrecked E-site. And it broke all the load cells because we were having to measure the thrust, and the thrust vector got load cells all over it, and they all broke. And this was simply the shock from that shearing breaking away and going onto the propellant surface. So after a lot of head scratching, Malcolm Paul essentially designed a hydraulic clamping system. So as this happened, the whole thing was locked very solid. Then we released the hydraulic clamping system and were able to measure the thrust alignment. There was minimal environmental testing to demonstrate the reliability of this thing. It was never tested at temperature extremes, for example, because as I've just described, it would never see any temperature extremes. A typical military store, you're required to demonstrate that it will work at plus 60, minus 40 centigrade. On this, it was all ambient. The worst mechanical environment that it was likely to test, experience, as I said, was on the road, on between Westcott and Coulport. So luckily, I believe, there was minimal environmental testing, unlike trying to develop a solid propellant rocket motor for tactical missile system, of which I've got lots of some good and some bad experience. Next, please. Thanks. Right, pointing accuracy was absolutely essential, as it is with any engine that's actually trying to reposition the spacecraft, whether that be an Apogee engine on a modern communications satellite or this thing. If that is not accurately pointed through the centre of gravity or where it's meant to be, it's essentially the centre of gravity in this case, then the AOX goes into overload trying to correct it. And you rapidly run out of AOX propellant, because it's doing something it's not meant to be doing. It's correcting somebody else's error. So pointing accuracy was absolutely essential on this thing. And therefore, because the nozzles on the engines are canted, they're aiming at different centres of gravity. They're not axial, they're both canted. Then there's a potential for uneven erosion in the nozzle throat, essentially, which could offset and cause some variation in the pointing of the thrust. So one had to find something that had zero erosion, and the solution to this was a sintered silicon carbide, and that came from British Nuclear Fuels Limited, who used it in their reactors. It did not erode at all, but after firing, and I always claimed it was after firing, it would always crack. And I invented a term called cracked but intact. So these nozzles at the end of firing were always cracked but intact. But that was essential. Each assembly, TCPU assembly, had its nozzle alignment checked with a complex jig. Put the thing in the jig, put a yoke-like arrangement, a bit like a big G-clamp, into the nozzle with a pointer, making absolutely sure that it was aiming within, I think, plus or minus 1 millimetre of the centre of gravity position that was predetermined, of course. Hunting engineering, gosh, I've forgotten where it is. Hunting engineering at Ampthill did all the structural testing of the pack unit. And under that, we found that under the simulated thrust, the yoke component, which held the two combustion chambers together and had the tanks attached to them, it was basically the central structural element. It was deflecting under engine thrust. So we had to do quite a lot of work to absolutely understand that and adjust the pointing target to compensate for that. On aerodynamic heating, as the nose fairing was taken off by the Westcott developed nose fairing eject motor, then the thing was exiting the atmosphere unprotected from that atmosphere, and there's a possibility, a likelihood of uneven aerodynamic heating on the combustion chamber bodies, which were aluminium alloy. And so to this end, an aerodynamic heating insulation, which was core, was bonded onto it. And I'm sure Mark will remember, we also had such a thing on a rocket motor called Remus that also had an aerodynamic heating protection around it. So that was just to prevent the possibility of uneven aerodynamic heating causing the things essentially to bend, cork insulation. Early flight models, the D standards, had an adjustable chamber to nozzle joint. It was a spherical combustion, spherical assembly with a big O-ring in it, and you could actually, at this range, you could adjust the angle at which these things were thrusting, because all the rest of the components were also under development, and therefore the centre of gravity wasn't particularly accurately defined at that time. And those D chambers, they flew from, yeah, they did. They flew from the Australian range, didn't they? Yeah, they did. As I say, a lot of this is all from my memory. Centre of gravity control is, of course, very important. We need to understand where the centre of gravity is and try to maintain it at that one place. So the TCPU had a pair of fuel tanks, a pair of oxidant tanks, and they were all running no matter which engine was running. So that was just achieved by the pipe work. So to try to control the centre of gravity as well as we could, we had that system, and carefully calibrated cavitating venturis, whose operation I've described a little earlier, they were in the propellant lines to try to make sure that the flow through them was dependent only upon the upstream pressure, which was determined by the hydrazine system and its high-level gas generator. So that was a very important part of it, pointing, as it is with modern-day apogee engines. Next, please. Security clearly was a very major factor. John mentioned it earlier. So when we were transporting this thing about the site, it was always covered up. That might seem far-fetched, but it's well known that satellite photography was such that you could probably see quite a lot of it. The total impulse was very closely guarded. You had to be of a high security clearance before you knew the total impulse available on this thing. And you would never fire the system to depletion, especially through the development missile launches. They never fired it to depletion, because anyone watching this could easily determine, that engine's just run out, therefore there's nothing more come, because it would die down, rather like a solid propellant would die down. But if you just turn the thing off, it turns off, and they don't know what else there might be. And of course, staff was subject to very high security vettings, and need to know was important. You might not know what the guy in the next office was doing. We were told to always assume that there was a spy amongst us. So yeah, that was important. Next, please. Okay, this is actually this picture is an extract from the paper I mentioned earlier on the PLTV. So it's actually a PLTV piston assembly, and it shows the PTFE slipper ring I was talking about. It shows the welded shear ring, and it shows the back-to-back elastomeric seals. And as you can see, that's a threaded assembly. It would be all welded on the TCPU. So that was very much the forerunner of the T11. Again, demonstrating that if you've got technology in the bag, you can meet requirements. Next, please. Here then is the final design. Now, it is sitting on its stillage, which was used to transport it about Westcott. You can see the two gold FEP bags. The FEP bags for the oxidant tanks would be attached to the pack, so that this unit basically sat in them a bit like a pair of trousers. You can see the two thrust chambers with their cork insulation and their conical nozzles pointing in different directions. The white metallic pipes are the fuel pipes, and the oxidant pipes, fuel at the top, oxidant at the bottom, feeding into that central yoke that I described, the beam into which they feed, which carries the poppet valves designed by Frank Henderson that would operate the engines, turn the engines on and off. Sitting below that and just above the aluminium plate is the electric junction box. The shiny pipe to the left as we look at it, that's the hot gas feed pipe. If you follow it through, you can see it feeds into the tank nearer to you. It goes across the unit and feeds into the tank to the right of you, and it bolted directly on to the HAS high-level gas generator. That's in pneumonic steel, such as you might build a gas turbine blade out of, and that would run cherry red. You can see the mounting ring, the perforated ring sitting on the aluminium plate. And then if you look carefully, you can see at the top coming out, I think they're PTFE pipe, little PTFE pipes. They are coming out of the secondary containment area into a collector, which you can see between the two thrust chambers. And that's the liquid current leak detection system. as I said earlier, it's part of the pack structure for the oxygen tanks, which are below. So there it is in all its glory. A very complex, difficult thing to design with, through its early stages, an ever-changing list of requirements. I can remember getting quite angry at sometimes having to change ratios and so on and so forth. So there's the final design. When Polaris came out of service, we got the contract at Westcott to decommission all of these. So it is said that none exist anymore. And the next slide, please. If you could run a little film now, Bob. This will be a film showing the system being fired horizontally at F site, and then the whole thing being fired at E site, where I described we had to have these hydraulic locks. So we could run that one.
So just to check, so that's the package liquid test vehicle?
No.
No, the other one,
yeah.
Royal Armies. Okay.
Yeah. I'll talk over it. You see, it is quiet, unfortunately. It comes from a very old VHS tape, which I haven't had there. Okay, this is the thing. It's upside down. This is the thing firing at an E site. You can see the nice, clean propellant flame there with its shock diamonds, and the flashing around there. That's the silica that I was talking about coming out of the nozzle. And then when that firing stops, you'll see flaming. That's some of the phenolic resin burning in atmosphere. You can see what happens there. This is the whole system, and you can also see it's got the gold bags on it. This is all one firing of the system. I think there's probably 3 pulses. This E site, by the way, is it's absolutely decrepit now. It's a great shame to see it, but it's the site on which the HTP kerosene engines were developed, I think, probably, that went on to power Black Arrow. John, am I right there? John, do you hear me?
Hang on, Paul. Yes, all the Stentors and Blue Steel were fired at each site as well.
Yeah.
And 605s, BS 605.
That's right. And I think it's been preserved as a heritage site now.
I think so, yes.
But it's absolutely falling to pieces. It's a great shame. And I do emphasise this is the film's upside down. We all slide it downwards at the east side. Yeah. And this is being run and is pressurized by. Oh, they marked. I didn't know that. This is being pressurized by the high-level gas generator from the HAS system. How much? Right. I think, Bob, we might stop that now and go on to, I think there's one more slide, isn't there? Yes. The final slide, for me. Right. This is by way of winding up. So having developed and put into service successfully this unit, liquid engines division, as it evolved, again needed a problem to solve. And one thing that we did, Dr. Alf Hardacre developed a pulsed unit in case penetration aids would need any propulsion, a program called from memory Zodiac Beecham. But that never came to anything. That could have been a massive piece of work for Westcott, but it didn't go ahead. But Dr. Trevor Horden, who I mentioned earlier, when he was in Washington, he identified the need for a so-called dual-mode apogee engine for commercial spacecraft. Not the engine that's dual-mode, it's the spacecraft. The spacecraft would have, at the time, would have an apogee engine running on monomethyl hydrazine and N2O4, and it would probably have an attitude orbit control system running on hydrazine. So it had two fuel tanks, two types of fuel on board, complicated, heavy. If one could develop an engine that would run on the hydrazine for the apogee engine, then you would simplify spacecraft design a great deal. Trevor identified that need, persuaded the then powers to be to see if we could develop that, and that development was successful. It became known as Leros 1. It was the world's first, and it flew on a commercial satellite called Astra 1B, operated, I think, by SES. And its successors are still in production. I hear that NAMO have just got an order for 5 1Bs. So that, again, having foresight and seeing that there might be a requirement is important if you have the technology base to meet that requirement. And I thought that in the 50th anniversary of Prospero, and the British government just realised that it might be a good idea to have a launch vehicle, I thought I would introduce that theme into this. Thanks very much. I'll take any questions or corrections even.
Right. Okay, so I'm just going to take over just for a second. So first of all, thank you very much, Paul and John. That was a really good talk. I was hoping it would be in depth, and you certainly delivered on that. We've got the same number of people at the end of the talk that we had at the start. So we know we've got the hardcore enthusiasts here, the ones who actually wanted to hear this. So here's how it works. So I'm going to just open up the chat now, and I see a few things going in there. Thanks, Mark, for putting the links in for me. When the screen share was on, I couldn't actually do it. So what to do is, if you've got a question, put it in the chat or try and attract my attention on the video. I'll try and do it in chronological order, and I'll ask you to unmute for your question, and you can ask it online, and then Paul and John can hopefully answer. Mark, also thanks for throwing these snippets of information all the way through in the chat as well. That's really useful. Thanks. So do we have any questions? You get a lot of thanks. A lot of people are very happy, but I think nobody wants to ask the first question. It's just what it is.
Okay.
Okay.
I would say something to Mark, if I may, as a hostage to fortune on my part. I've actually got a talk that I give locally. It's a Peter and Jane description of Westcott, rocket motors at Westcott, and so on and so forth. It has about 80 slides, so I do talks sometimes.
Excellent. We may be calling on you again.
Well, it's very much out of date now, unfortunately, what with reaction engines and the changes there, and Bloodhound, the changes there, because I use that for hybrid rocket motor, finding a solution, finding a problem. But yeah, so I do talk sometimes.
Oh, thank you, Paul. Would you excuse me for 2 minutes, and I'll go and get a combustion chamber, and I'll show the combustion chamber.
Right.
Okay, while we're doing that, we have a question from Ian Johnson. Ian, do you want to unmute and ask your question?
Hi, Ian.
Hello, Paul. I haven't seen you for a few years.
No,
I was just wondering, a bit of a side question really, but where does the name Chevaline come from?
I don't know, but I can remember. Do you remember that mysterious murder in France? It was never solved when the people was shot. That was actually in a village called Chevaline.
Ah,
And out of curiosity, on a motoring holiday in France once, I actually visited the place. But the answer to your question is I don't know.
okay, it's curious. I know there was antelope and super antelope,
Hmm.
and I had heard that Chevaline was supposed to be a kind of antelope, but in fact it's French for horse butcher.
Yeah.
I remember Stan Green sending a photograph back from his French holidays with him standing outside of Chevaline butchers saying
right.
major security leak.
Yeah, well, say there is a village called Chevaline.
Yeah, I remember
It's
that.
up near Lake Annecy.
Mhm.
I wonder whether Gary George could add some information as to the naming. Gary, can you hear us?
I'm not sure. Can I be heard?
Yes,
Yes.
gotcha.
Yeah, Chevaline came about, and it is related to antelope, super antelope. And without giving away all the story, one of the mandarins in London asked one of his colleagues, could we come up with a better name for our new program? And this chap happened to have a colleague who worked in London Zoo, and phoned him up and said, do you chaps over there have a big antelope? And he says, well, we've got this thing called a Chevaline. I think it's a South African beast. And that's where the name kicked in.
All right. No, never knew that.
Barry, when you wrote it in the chat, I thought you were joking.
I never joke. Same as
Okay.
I would say I would never use seawater as well to flood. I'll leave it at that. And Zodiac Beecham was a great success.
Luckily never used. Next up, John Boyce. You've got a question. Do you want to unmute yourself and ask?
Okay, thank you. First of all, many thanks, Paul, for a most interesting talk. One question. How many times could each TCPU chamber be fired?
In service, it could be fired twice. It would be fired twice, so that was a capability. If you could fire it many times, I don't have a precise number, but you could turn it on and off, and you could pulse it as well. One of the PLTVs flew essentially a sawtooth profile in velocity terms by pulsing the engine. So you could do many firings on it, yeah.
Thank you.
Okay. Next up, Martin Westwood. You have a question. Would you like to unmute and ask?
Hello, you got me there. Okay, it's a message for Paul, I would guess. And well, thank you for the talk. When I first picked up on Chevaline working for Doughty Bolt and Paul, the yoke assembly and valve assembly was all made from one casting on the development, and that was very difficult to produce. This was later changed to a 3-part assembly,
Yeah.
where we had a right-hand valve, a left-hand valve,
Yeah.
and we had a connecting yoke.
Yeah.
It's very interesting for me to hear about the measurements and testing done at Amptill with Hunting Engineering, where they found deflection in the assembly under fire.
Yeah.
Do you think that making this a 3-part assembly was the cause of this deflection, where, as in casting, the webbing, the natural webbing from a casting would actually strengthen the yoke in itself?
Yeah, well, you certainly accurately described the final solution, which was the 2 valve blocks into that central yoke. From memory, the yoke main structure was quite a quite a slim aluminium component structure, maybe 10 mil in thickness. Yes. And when Hunting's reported that the thing was deflecting, our first thoughts were that it was the combustion chambers themselves that were deflecting, but upon closer inspection, we realized that the yoke was kind of twisting. So maybe a cast structure with some cross webbings in would have prevented that. I don't know, but yeah.
Sure, yes, yeah. As an apprentice, my first metrology project was to actually check out this one-piece unit and to do all of the measurements and check it was all right to drawing. But we only ever made a very small amount of them.
Yeah, I don't think it went anywhere, the cast unit. It was always fabricated. So were you involved in what I was describing, measuring all the impingement points and so on?
Yeah, I knew very well a guy called John Barber who worked at Westcott. He was sent from Doughty Bolton Pool to actually do the measurements with the pins.
That's right.
And we used to send the valves for measurement, which we call metrology check.
Yeah.
And then there was a patternization check done at the same time, as you earlier described. And then I had to do an awful lot of work after that to get them ready for assembly. And
oh, right. Well,
it was very, very few, if any, failures on metrology after the initial problems were sorted out. It was actually a very successful project.
Yeah, you'll remember then how the profile of the inlets, where the fuel inlets were actually profiled, and the oxidant jets relied upon the bore of the valve itself for that coefficient of discharge, and that's why the internal bore had to be very finely machined.
Sure, yes. This was all in the days pre-CNC machining.
Oh, yes, indeed. Yeah, we go back a long time, yeah.
Yes, we do. And indeed, each of the injector holes, the 1 millimeter injector holes for the fuel and the oxidant, for each hole we could only use a drill for 3 injector holes, and then we had to replace the drill bit every 3 injectors.
Yeah. Well, I mean, just conversationally, the NAMO, as it now is, at Westcott, build very, very small attitude control engines, and some of the fuel holes in that are 4,000.
Wow.
And you use the drill once. And they have a specialist machine from Hawley Drill Services to drill those tiny little holes.
Sure, yes. Yeah. All good things. We could talk for hours, but there are other people. Yes, yeah.
So next up, I just want to a comment from Robin Brand. He was saying, as a point of information, last time he was at the FAST Museum in Farnborough, he said there was an object that looked very much like the pack that you showed. Right, next question I've got is from Keith Burrell. Keith, do you want to unmute and ask your question? Keith, you're still muted. I'm going to ask you to unmute by clicking the Ask to Unmute button. No mute. Okay. Right. So Keith's question. Have you any thoughts about how big a difference it would be applying current electronic software, artificial intelligence and material science to your previous project would have made in terms of performance improvements?
It's a good question. I can remember, and John will remember, one of the brain boxes of this whole program is a guy called Roy Dommett. I can remember Roy telling me that when he was designing the system and its systems attributes, if he needed a piece of electronic control, he assumed it would be available. And in other words, control systems, electronics were advancing so fast that he could just assume anything he needed would be available. It doesn't exactly answer your question, but what do you think, John? I don't know that it would actually. Don't know that it would. Wouldn't have affected this to T11 that I can think of. What would have affected it is 3D printing and the manufacturing capabilities therein. You know, we could make much more complex galleries for the liquid propellants and so on. And I've seen such work at a local company, making things just impossible otherwise. So that would be a significant advantage, I think.
Mm-hmm. When you see the film next month, the one that Airborne's been testing, it's a ridiculously complicated looking device, and it's all single. It's just a single thing, single manufacturing component. Absolutely fascinating. You've got to watch that film next month. Anyway, next, I think John Bonser. John, do you want to unmute yourself and ask your question?
Yeah, that's me unmuted. Can everyone hear me all right?
Yes.
Okay, thank you. Well, first of all, just to repeat what I said in the remarks, thank you very much, John and Paul, for a fascinating talk. I like the way that John set the scene, and then you told the story in great detail, an awful lot of detail in there. I normally take notes while these talks are going on. What I did in your part of the talk, Paul, was I just jotted down what I thought were the essential points, and I'll try and fill in the gaps later. Just absolutely fascinating. But my question is, I imagine, of course, at one time all this must have been very much on the secret list.
Yes.
And obviously it's come off the secret list now, but I imagine there must still be aspects of the Chevaline system that are confidential. And I'm recalling that just before one of the Brock conferences, the Rocketry Oral History Program conferences, I think it was either 2002 or 2005 that I was at, there was a bit of a controversy in apparently the Australian press, because they got hold of the fact that the Chevaline test trials had been done at Woomera, and this seemed to cause some discomfort amongst some circles in Australia because it was connected with the British nuclear deterrent Polaris program. I think that my recollection, can't remember all the details now, but the point was that I think there was going to be something said about the Chevaline system at the Brock conference. John, you might remember that. But my question is, how long has the detail you've been giving us today been off the secret list? And are there still aspects of the system that are still secret?
First of all, yes, it did get tested from Woomera.
Yeah.
I think very little of what I've said would be on the secrets list. I did mention thrust levels. I didn't mention total impulse requirement.
No, you said that was never revealed.
And that was a very, very not a great deal of it would be very highly classified. And as I said, the hydrazine system that controlled everything, that was an unrestricted, unclassified program. It had to be, because it involved many, many United States companies.
Oh, well, perhaps the fuss in the Australian press was more manufactured than...
Yeah, I've got no knowledge of that.
I knew the
political thing at all.
I have a poster, so I think you gave to me, Mark, at a Brock conference, of Chevaline test firing. It's a rocket with a bulbous payload section carrying the Chevaline devices, being launched by a stone shaft motor with very large fins. I have that poster prominently displayed on my rocket workshop room walls. Other stuff I've gathered over the years. I might even make a scale model of it sometime. It's quite a nice thing.
Yeah, the stone shaft motor powered Falstaff, which was used, I think, to develop some of the components, the atmospheric re-entry system, and so on.
Okay. Well, thank you very much. Thank you.
Okay.
Reading from the comments, so Ian Johnson saying there's apparently a complete pack at Gosport Submarine Museum, and he thinks also at Bristol. So are there any more questions? Pete, I'll let you go first. Do you want to unmute?
Good afternoon, and thank you, Paul. Thank you, John, and of course, thank you, Chairman. What I really wanted to do was just add a little bit of further information about those test firings at E-site in particular. We need to remember this was before the world of computers. We were spewing out paper from paper recorders at something like 2 meters a second to capture the data with mirror galvanometers done in the dark, so he could subsequently develop those records in conjunction with WeDram. And further to that, another more sophisticated system that utilised an online data recording system, one of the first PDP-11 mainframe computers.
Yeah.
Of course, all that was after all the relatively laborious, to us young folk at the time, of the calibration of either pressure transducers, load cells, thermocouples. A lot of background work goes into each test and each subsequent firing. And not only on the firing officer, but on that backroom team who are desperate to capture all that data and subsequently present it. So yeah, really was a bit of a team effort in those days. But thank you again, Paul. Excellent talk.
This is you're very the picture I see is very dark. Is this Pete Hammond?
It is.
Oh, hi, Pete. I thought I recognised the voice. Yeah, well, you're right. When at eSight, when we doing that, there was so many channels, and there were 2 WeDrams involved actually. Yeah. Oh, nice to see you, Pete.
And you guys.
Yeah.
I can add another story to that, guys. At the Cape, they were still catching up with data reduction and modern electronics, I'll call it that. And there was a telemetry station called Tel4 that had well past its sell-by date. And one of the UK team always had to be in Tel4 during one of the Polaris shots, and Chevaline shots as well. And the problem there was that it was quite a small, probably just the size of this room, and it was full up with paper recording instruments. And when the flight actually got going, all of these things spewed out miles and miles of paper. You couldn't find your way out the building. It just, they were surrounded with paper. Dear, oh dear. Things have changed somewhat, thank goodness.
Yeah, on the film at Westcott, Airborne were sampling their tests at 10,000 points per second. And then, so they've got all this data, it's all a computer, and then it's analysed, most of it automatically. Really interesting. Right, just before I go to Mark, I'm just going to read a question from Alex Wood. Alex asks, do we know how much the Soviets ever learned about Chevaline?
No. I've always had a thought that this is a deterrent, right? It can only be, in my view, this is not to be taken seriously. It can only be a deterrent if the other person knows what you've got and what it can do. We strove really hard to make sure they didn't. So the deterrent, they must have found out what it could do and how it would do it, thinking that they'd stolen that information, but in fact we were giving it to them. Otherwise it's not a deterrent, is it?
That's kept everybody quiet.
I don't know, it just occurred to me.
Okay, Mark, you're on.
Paul, do you recognise this?
Yeah, that's that. Yeah, that's one. Well, not that one, but that flue. Yeah, that's the adjustable nozzle.
Yes. Yes. So,
the cork insulation.
Yes.
Yeah, it's got a big silicone O-ring in there to seal it.
Yeah, down in there.
Yeah, and you can actually adjust it with little adjusting screws. Some 3 legs, I think there is.
Yeah, there's there, and there.
Yeah, you can actually adjust the angle of the nozzle. Yeah, I do. Where'd you get that from? I don't answer that.
So just to give you a bit of background, my time on Chevaline, everybody, was I was recruited from the design office at Westcott, and I went into the liquid motor project office to work on in-service surveillance, which is the long-term storage and surveillance testing of the beastie. So that was my background. But again, I was the junior person, and what used to happen was if they needed help, because I started out on the shop floor, so if the assembly people needed a hand, I used to get posted up to TCPU assembly, and I spent plenty of time wire locking bits onto the TCPU and fiddling around and fitting gold bags, which was always a good game because you mustn't get fingerprints on the gold bag and get into all sorts of trouble for that. And also I was one of the sort of troubleshooters. So Paul, do you remember the problems that occurred with the hot gas pipe? So there was a seal on the hot gas pipe that used to get stuck, and Coolport, when they were servicing and taking the things apart, used to get these the seals stuck in the hot gas pipe, and this got reported as a problem, and I developed a little tool that I then wrote a little manual, a little set of instructions for. It was all sent up to Coolport, and they went, "Oh, not using that." And so I had to go up. It was me that if they got stuck, I had to go up there and use this tool.
To be honest, I don't remember that, but was that the seal between the hot gas pipe and the high level gas generator?
Yeah.
No, so I don't remember that. Mind you, I probably had moved on by then. I don't know.
Yes. Yeah, because I was a late entrant into the program, so very late. So.
Oh, that's a shame, because Mark would have put his heart and soul into that.
It was quite an experience going up and working at Coolport. It was a very
different,
very different and very, very secure base. And if in fact the base is still there. I holiday in Scotland quite a lot. My wife and I holiday in Scotland quite a lot. And if you get there's a paddle steamer that goes up
Waverley.
The Waverley.
Yeah.
And you can actually go past the Coolport base, and it's still there with all the double fencing, and you can. It's a most bizarre experience because you can stand on the Waverley with a pair of binoculars and look at this base which was so highly classified. It was really another experience in there, even down to an inner base where there were Marine guards, fully armed Marine guards on guard all the time, wandering around. It was an interesting experience. Yes. While I'm on, Pete Hammond, we're trying to organise a propulsion conference next year. Would very much like a talk on how to run a solid rocket motor firing facility safely, please. If you're interested, it will probably be at Cosford in early April, a Saturday in early April. So please do have a think.
I'll trust you to hijack this meeting, Mark. Yes.
Yeah.
Right, we do have more questions. Right, next question is from Alex Wood. He's asking, did the Soviets ever have anything to counter Chevaline?
John's
They'd have got enough SA-12 plus interceptors, yes. It would have done it. Well, even put in a new cup at the beginning or halfway through the NRV would wipe a lot of the stuff away. So it was obvious what the real beasts were. Think about it.
Okay. Alan Marlowe. Alan, do you want to unmute and ask your question?
Yeah. Did the Americans adopt Chevaline, or did they have a similar system, or did we have to develop it because they wouldn't share some system that they had with us?
I don't know the answer to that.
I can only quote what I think Domit said once to me, that they had antelope, and studies with the UK came up with super antelope, which we adopted in form, and it became Chevaline.
Are we allowed to mention where the HAS system came from?
Yeah, it was all completely unclassified.
Yeah, it was off Peace Courage, wasn't it? Off the Minuteman.
Yeah. Well, some of the elements were off the Minuteman Stage 3. Yeah.
Yeah.
And the rest of it was it Mariner 9 or something? Some of the bits were off Mariner 9.
It was what?
Some of the bits were off Mariner 9, NASA
were they?
spacecraft.
Yeah,
that orbited Mars.
basically, the company at Niagara Falls Bell Aerospace Tech Plant stitched together that system using components from here, there, and everywhere. Some components were purpose built, especially the tanks by a company called Harlow in New York. But yeah, it was in place technology, and it was just a stitched together system. But you're quite right. They did all the propulsion on Minuteman Stage 3, and a lot of that experience was read across. Yes.
Is it worth saying a bit more about the IPN system? Because IPN gas generators are used on CDART, for instance.
Yeah.
But it wasn't my limited understanding. You two know much more about this than me, but my limited understanding was that they couldn't. It wasn't the system that they came up with for IPN on Polaris wasn't man enough. Is that correct?
It would have shaken the pack to bits for a start.
Yeah, it had a crazy reciprocating valve arrangement on it, and when it was running at a site they ran it, it was like a Gatling gun going off. You could hear it all over the camp.
Went faster and faster and faster. Yeah.
Yeah, it was it would have benefited a great deal from 3D printing because it was an enormously complex machine. I can remember me and Dudley did a pressure budget for it, and decided that it was never going to be man enough for the task. But I was not particularly senior person at that time, so I wasn't involved in any political or high-level commercial discussions like I might have been later on. I just know that I got to join Dudley on the HAS team, and that was, well, it was difficult, but it worked.
Dudley was difficult.
Dudley, I was at his funeral not long ago.
Okay, so next question is from Martin Westwood. Martin, do you want to unmute yourself? Also, I think you found some Chevaline units about the country.
Yeah, hello, Bob. Yeah, yes, I've got a bit of a hobby of hunting down Chevaline units. And I know Mark's got a few, and I found him at Hampton University with one of them. Very nice. Yeah, my question, we did some production batches A, B, C, D, and so on, of propellant valves and injector assemblies, but we also did some batches, I guess, for test firing. There were additional units. How many of these were actually used for test firings, and how often were test firings made throughout the life of the Chevaline units?
Did we do in-service surveillance? Did we do it? I don't think we did we, Mark? In-service surveillance. In other words, did we take some out of the stockpile and run them? I don't think we did, actually.
Yes, yeah, that was...
We did do.
Yeah,
I'd moved on
every other year one would come out for firing, and one during the program while I was involved, it would come out for firing, and the other year it would go through all the environmental trials, and then it would be cut up by John Aldred. Yeah.
John Aldred.
There was an extensive set of environmental trials that used to go on, which was me, and involved time up at Bishopton. Used to take, which John, if he's still here, John knows Bishopton. So I used to take Tcpu up to Bishopton and vibrate it. Road transport, flight vibration.
Yeah, like I said, road transport being the sort of design factor.
And of course, we had a problem with the burster discs on the oxidizers tanks during that period, and that caused quite a fuss because that was the the containment side.
I think I supplied a list of at least, I've got here in front of me, 23 submarine shots, which include everything from PS1 right through to the end of the third demonstration and shakedown operation. So that's from the sub launches. Of course, there were pad launches, and the 3, I think, at Woomer for the TCPU. That's just TCPU data.
Yeah.
It should be on the web if anybody looks it up.
Okay, so I think we're drawing to a close now. Are there any more questions before I close this meeting? Okay, I think we're there then. So everyone, I'd like to say a big thank you again to John and Paul for today's talk. It was really great to have this knowledge kind of documented, the unclassified version of it. And thanks for all of you other people from who've worked on the Chevaline program for piping in and sharing your experiences and ideas. So the usual crew, in a moment, I'd like you to stay on. We'll just do a wash up if that's okay. Paul, if you could stay on as well, that would be great.
Yeah.
For everyone else, thank you so much for supporting us today in our event. Don't forget to go onto the BIS website and register for next month's event. It's going to be amazing, I promise you. It's going to be good. And I hope to see you next month.
I'll be right back, Bob.
Okay, that's fine. Okay. Bye, everyone.
Really good.
Bye-bye. Thank you.
Take care, everyone.